Good morning.
Hold on.
Hey, good morning, Daniel.
Morning, Dr. Chris.
How are you doing?
All right. It's been raining here since yesterday, actually.
Yeah, did it rain on Sunday there also?
No, it didn't rain Sunday. It was cloudy, but it didn't actually rain. But it started Sunday night.
Yeah, I think that's pretty much what happened here. It was maybe supposed to snow this morning, but I don't think it was cold enough. I think it just rained. Yeah.
Glad it did it.
Yeah. So are you in ROTC? Is that what you said?
Yes, I am.
Do you guys have to like plow the sidewalks at ISU or anything?
No.
Okay. Maybe that was just where I did my undergraduate was at Colorado State University. And for some reason, the ROTC cadets, they had to like plow the sidewalks, which meant that
Wow.
if it snowed, they had to get up at like 3 a.m. to start plowing.
Oh, yeah. I did that when I worked for the maintenance crew on campus. We had to like plow every time it snowed.
Yeah.
It was not fun.
Yeah. Yeah, I remember there was one guy in ROTC in our chemical engineering class, and every day it snowed, he would just be so tired. So glad you don't have to do that.
Me too.
Yeah. So, good morning, Cade.
Good morning.
So how long did you work on the maintenance crew, Daniel?
I was with them for about a year.
Yeah. Yeah, it sounds like it'd be like kind of fun, but too much work.
It's fun when you're like doing indoor stuff, like doing handyman stuff, building. When
Yeah.
it comes to like landscaping, like
Yeah.
when the leaves fall, you have to like break everything and stuff like that. It got tired.
Yeah. Yeah, when I was in college, I worked for a summer as a maintenance worker at a reservoir, like a lake reservoir in my hometown. And it was pretty fun, but the worst part was that like people would go fishing and they would catch carp, but they didn't want them. And so they would just leave them on the bank. And then whenever we found them, then we'd have to like clean them up and they were so gross.
Whoa.
So I'm glad I
Whoa.
don't do that anymore. All right, well, it's 8:01. So yeah, good morning, everybody. So I think you all saw the announcement because you're here today. Yeah, I apologize. I had a personal matter come up, so I had to cancel the class on Thursday. And so because of that, I thought it would be a little more convenient to cancel the quiz this morning so that we could spend a little bit more time, that extra 20 minutes together working on the homework. So I think you all saw that. And then let me just point out as well. So on Thursday, since I will be gone, I made some extra videos, or I have some extra videos that I've made. So you can find those all here. Okay, so can you see my Moodle page? All right, so if you click here, there are these ones, and then, shoot. Oh, okay, sorry, here it is. On homework 8, this is a problem from homework 8, and this is a problem from homework 8. So I've basically gone through these two problems the way that we would do them in class. All right. Okay, and then next week, when I get back next Tuesday, we will review. All right, so we'll do a review of all of the magnetostatics and the time varying electromagnetics. And then on Thursday next week, so on 11/4, you'll have the exam 2. Okay. And so whichever place that you went to take the exam 2 or exam 1, that's where you will take the exam 2. So everyone, I put in the requests yesterday, but I requested for Cade for you to be in Idaho Falls and everyone else to be in Pocatello. So hopefully that still works. Okay, any questions? Okay, and then by the end of today, I'm probably going to add 1 or 2 problems to it, but I'm going to make this exam 2 practice problems. I'm going to make this live and I'll make an announcement, but this will cover some additional practice problems on magnetostatics and time varying electromagnetics that you can do prior to the exam 2. So hopefully that will help you. And then I'll make this available so that if you have any questions on those problems, we could work on those problems during the review day. All right. Yeah, so questions, comments? Did you all start looking at the project? Did anyone purchase anything or come up with a potential design, have a route that you're thinking of going already?
I had some magnetic tape.
Oh, interesting. Okay.
Taped it to inside of like a box
Okay.
of cards, and then I have a nail that I put through something on the end so it can rotate.
Yeah, that sounds like a good start. So cool. I saw a thumbs up from Gabriel also. So if you have any questions, send me an email or just let me know. And like I mentioned, I think if you do think you need a supply, I recommend you purchase it before the end of this week. So just gonna put that out there again. Yeah. Okay. So if there's no more questions, let's do some homework. All right. So we did not get to the last problem on homework 7. So let's take a look at this one. All right. All right, so we have a coil and it consists of 100 turns of wire wrapped around a square frame of sides 0.25 meters. The coil is centered at the origin and each of its sides is parallel to the X or Y axis. Find the induced EMF. So this is the EMF voltage across the open circuited ends of the coil when you have 3 different magnetic fields. Okay, so first, on your piece of paper, see if you can draw up what this coil of wire looks like. So choose a coordinate system, make your axes, draw the wire, and label the sides. Okay, so take a couple minutes and do this on your own piece of paper. Were you able to get something drawn up already?
Yeah.
Okay. So I'll just draw my own sketch. I won't draw all the loops, but let's say it looks something like this. Okay, so these are the open circuited loops. They have an X and a Y. The square frames. So this height should be what? 0.125 meters. All right, is this what you all got?
Yeah.
Daniel? Good, thumbs up.
Yes.
Okay, cool. So, all right, so now what should we do to find the EMF voltage on this? What strategy do you think we should use? Well, how about first, is there, right? Remember we had two different types. Is it transformer EMF, motional EMF, or both? Okay, so give me a thumbs up if it's transformer EMF. Okay. 2 thumbs up, 3 thumbs up. So there's definitely transformer EMF. What about motional EMF? Is there any motional EMF? Give me thumbs up or thumbs down. Yeah, no motional EMF. Right, these loops are not moving at all. So we should be able to find this voltage, right, by using this relationship, right? And this is equal to this. This is all looking correct so far?
Yep.
Okay, so if this is the case, now on your piece of paper, see if you can find an expression for the EMF voltage. All right, so see if you can find an expression now for the EMF voltage. All right, so what is the result of this integral going to be equal to? You want to tell me?
Give me minus 20 over 3 into negative 3.
Okay, so is this in this integral? Are we going to integrate the
Sorry.
so maybe the other question I'm asking is this a constant?
Yes.
Yeah, so let's just pull that out. Okay. All right, so what is this equal to? How about that? What's this integral going to be equal to?
0.065.
0.25 or
The limits for it, not from negative 0.125 to 0.135.
yes, and oops, I realized I made a small mistake here. What the heck? So yes, that is what the limits are. But do we need to do the whole integral? Do we need to do this integral? You can if you want, but we could also realize, right, that the side is 0.25. So the area is equal to the side length squared. And this integral, right, is equal to the area. Okay, so given this, I'll give you a couple more minutes, see if you can get to a final result. Okay. And once you have the final result, upload that to the Google Drive. All right, do you need more hints? Haven't seen anyone's upload. Are you close?
Yeah, I'm having trouble accessing the Google Drive.
Okay, do you want to just tell me what the result is that you
Yeah,
got?
I have 375 e to the negative 3t volts.
All right, did anyone else get the same thing? All right. Okay, perfect. All right, so the only other thing that I will ask you is based on this, based on the way that we did this, how did we define what the voltage across here? So which side should we label as plus and which side should we label as minus? This is kind of outside of the problem doesn't actually ask for this, but it's a good check to see how your understanding is. So we have two, I'll draw it in red so you can see for sure what I'm talking about, right? We have these two terminals, terminal 1 and terminal 2, and we should choose labels for them as reference. So one should be a plus and one should be a minus. So which terminal should be plus and which terminal should be minus?
I'll make one minus.
Okay, so why would one be minus?
My reasoning is that the current travels through the negative direction.
Okay,
That's the negative x.
all right. I think Gabriel, do you have a reason also? Saw your hand was raised. So what should one be? What do you think one should be?
One will be minus.
Okay, and what is your reason?
Because the current will flow from 1 to 2.
Okay, but when we define the plus and minus, right, we're defining it based off of something. And what are we going to define it based off of? So what did we choose DS to be? It was Z hat. Okay, so based on our DS, what's the direction that we used for this integral? So if I put my thumb in the Z direction and then look at this problem, my fingers, they'll point in from plus to minus. So which one should be plus and which one should be minus?
So 2 would be plus, 1 minus with the right hand rule.
Okay, so the Z, so yeah, okay. So is Z coming into the page or out of the page? Maybe that's what the confusion is.
Oh, I had it out of the page.
Yeah. All right, so if Z is out of the page, your fingers are pointing in the plus to minus direction.
Yeah.
We'll get 1 as plus and 2 as minus.
Oh,
So they point from plus to minus. That's the direction that your fingers should be curling in. So it can change, right, over time, right? So like for this problem, the reason that we need to have a reference like this is because we're going to come up with one answer, right, for V. So when we get to this result, right, we've said what V EMF is, but V voltage, right, voltage is a potential. and potentials need references. Right, so you need something to reference what the potential is. So the potential at one point with respect to another is a shorthand for what we're always saying, right? So like when you're working on your breadboard in the lab and you have a ground, right? You're just saying everything is referenced to that ground, right? That ground is, I mean, I guess you can say it's 0 voltage, but compared to the universe, it might not necessarily be 0, right? But your whole breadboard is you're just referencing it to that ground. So you always need to have something that you reference. And this problem, right, this one's a little bit more simple because this is this function is only changing in one direction, but on these other two, right, these have sines and cosines in time. And so the voltage is sometimes going to be positive in one direction and negative in the other direction. So the reason that we need to be able to know what the 1 and 2 are is so that we have a reference with respect to something. And we get that respect by determining what this ds is. So we used our right hand rule and the fingers will point from plus to minus. And that's how we'll always be able to come up with the reference. Any questions on that?
How do we decide if z is going into or out of the?
Okay, so this here, this is always how Cartesian coordinates are set up. So you can use your fingers or just rotate this in your brain and realize that the z, if you have, like, you know how we're normally, probably from the first graph you saw, it was given like this, x, y. So if you rotate that in your mind, right, you should, what you should be able to realize is that the z is pointed out of the page for this classic XY axes set. Anyone else have any other method for remembering?
So could we, since we see that the magnetic field is a positive z direction, and if it was negative z, then it would be pointing into the page.
Yeah, that works also. Yeah. So that could be another good way to help out. So positive z is out, negative z is in. All right. Yeah, so that's another way you could think about this. Okay. All right, so do you want to do one more of these or move on to a different problem? What are you all feeling?
Can we do one more of them?
Yeah, let's do B. It's a little bit more difficult, right? It has both spatial and time varying properties to the magnetic field. Okay, so we got this. Now let's go back and check. Has this situation changed? Are we going to have transformer voltage, motional voltage, or both? What do you think? So give me a thumbs up if you think we're going to have transformer voltage. Yeah, so we definitely have transformer voltage. What about the motional voltage? Thumbs up or thumbs down? Okay, we got one thumbs up, one thumbs down. All right, tiebreaker. What do you think, Daniel?
I think we'll have.
Okay. Let's look at the problem then. So transformer EMF happens when we have a time varying magnetic field, but a stationary loop. Motional voltage happens when the loop moves, but the field stays constant. So we know for sure, right? We can see our field is a function of X and time. So this one is definitely moving. We definitely have transformer voltage. But what about the loop? Is the loop moving in part B? Does the loop move? So for those of you who said you thought there would be some motional voltage, I'm guessing you thought it because we have this X, but does this X refer to the loop or does it refer to the field? Yeah, this is for the field. So is there any motion in the loop?
No.
Yeah, there's nothing to indicate that this loop is in motion at all. All the case that we have here is just that the magnetic field changes in the X direction. So we could think of this too, right? What does this really mean? We don't really need to know exactly, but let's just remember right from we did some arrow plotting in the beginning. So this is a cosine of X. So let's see. This just means that some places, right, we have a field. The field is sometimes positive and sometimes negative in that Z direction, right? So this is actually going to be a little bit confusing, but sometimes, right, this part only is going to mean that some parts of this field are positive and some parts are negative. That's more or less what this means, I suppose. So this is the field. And this is only looking at the, I don't know, time is equal to 0. All right, so this is describing the field, the change in the field only. So now that we've determined that we have no motional EMF, we just have the transformer EMF. So for this problem, we'll solve this same integral and spatial integral and time derivative. And right, this is still minus 100. All right, so see if you can solve this integral. All right, and the hint, right, that I will give you to start is check to see, right, we have this time derivative that's way outside, but then on the inside we have this spatial term. So see if you can use that to help separate the integral a little bit and find a result for this integral.
I got 5 sine of 0.25 cosine of 10 to the third t.
Sorry, and this was is 5 sine. Did I get this right? I'm
Yeah, I got sine of 0.25.
yeah. All right. Did anyone else get this? Give them a moment to work through that. And then did you find an answer for what sine 0.25 is?
It was 0.247. So
Yeah, 0.247. All right. Did anyone else get this? Thumbs up if you got the same thing. Daniel, Gabriel.
Okay. Something different.
Something different. All right. What did you get, Gabriel?
1.091.
291.
091
091. 1 point.
times 10 to the third minus 3
Times.
minus
Okay.
that's -3 in the exponent.
Okay. All right. I'm not quite sure what you got. So this is another something like this might be another possibility. So let's go on and check. So this times 100. All right. So if we either way, right, we should end up with a DDT that we have to take, right? This 10 DDT of this cosine term. So let's see. I think that maybe the final result should be something like what I'm getting is if I take this term, we could simplify this a little more to 1.237 cosine 10 to the third t. And I think the final answer is like something like 1.23. So I think this one is on the right track. So let's see if we can keep going and get to the final answer here. So if you haven't, take a minute and do this derivative. Okay, so take a moment and do this, and we'll set this aside for now and check later. Let's just see if it's the same. But let's do this. Let's take this derivative now. right, this is what I got. Anyone else?
Yeah, that's what I got.
Okay, so. So then, or this should be one. And was this the same thing you got, Gabriel?
Still working on.
Okay. Oops. And I think that was, sorry, that's a mistake there. All right. So I think this is what I got also. So hopefully this is what you get when you work through the final result. But basically, right, hopefully what you're seeing by now is, right, to solve these, first you want to determine if you have transformer voltage or motional or both. Then two, you want to define, you want to make sure you have a defined reference, right? So you want to define your reference voltage. And you do that with DS. And either way, whether you're doing, whether you have motional or transformer, you're going to need to define that reference voltage so that you know which way to reference it to. And then depending on whether you have the transformer EMF or the motional EMF, solve using the appropriate equation. Oops. Now, what also to remember about this is that this one always works. Right, this one can be used for the transformer and the motional. However, the motional one, right, that one does not work for every single case. Okay, so, right, so when you use the motional equation, then you have to make sure that it works. This one will not always work for you. So this U cross B DL This one does not always work. This one is for motional only. Okay.
So, the question,
Yes, yeah.
for the previous problem, you meant to take the angle radians, not degrees.
Ah, okay. Yes.
Yeah, just wanted to clarify that.
Okay, that makes sense. So this one was incorrect, and make sure when you're doing this, so make sure to use, so your calculator should be on radians. So use the radians. Right. So that's a great point. So if, right, in these given problems, just generally, right, if we have something like distances or whatever that end up going into cosine or sinusoid, if they aren't given to you in degrees, you should make sure to use radians. So that's a good point. Okay, any other questions?
Didn't get what Gabriel said.
What he said?
Didn't hear him.
Okay, he said he was accidentally in degrees, not in radians. Yeah. So that's where the small mistake came from. So I think he had done the problem just about correctly, but may have used the degrees on accident. Okay, so let's move on, and I'll give you a couple more hints. So let's look at homework 8 before we go. So we have what, 20 minutes? So this one is number 8. Okay, so we have a square loop. It's coplanar with a long straight wire. And we want to determine an EMF across a small gap in the loop. So there's a small gap somewhere that's been created. So maybe from here to here. And we want to determine what the EMF induced across this gap would be, and determine the direction and magnitude of that the current would flow if you replaced the gap with a resistor. And we want to know it at time is equal to 0. Okay. So this problem, right, the reason that this small gap idea comes into play is that we don't actually have a gap, but we know that there's some EMF that's being induced on it. So we're just going to pretend as if there is a gap so that we can get this, so we can get the answer. Okay, now we should notice how many, or is this motional? So is this transformer or motional? So is the loop moving at all? Is there anything that we can see that indicates the loop is moving? So is this loop of wire moving?
No.
Yeah, so it must all be transformer EMF. And we know that, right, because if we were to replace this, we have this phi. And if I replace this current amount, over 2 pi r. Okay, Now, what about one more question? So is this loop, is there any way we can simplify this problem at all? So which coordinate system should we use? Cartesian or cylindrical? So look at this problem. It's given in Cartesian here, but we have this convenient expression. This is a well-known expression, right? For the magnetic field due to a infinitely long wire, and this is given in cylindrical coordinates. So which coordinate system do you think will be best for solving this? So is that cylindrical, Gabriel? Is that what you said? So give me a thumbs up if you want to do Cartesian. And then thumbs up now if you want to do cylindrical. Okay. So 2 cylindrical, 2 Cartesian. Now let me give you some ideas about why I think that it might be actually easier to do this in the cylindrical coordinates. Okay. I mean, I apologize, in the Cartesian coordinates. First, on this plane, what plane is this loop in? It's the plane of the loop
YZ plane.
is in the YZ. Okay, so with your right hand rule, so put up your right hand and figure out right on this plane that the loop is in, what is phi? What is the phi? If you look at just that plane that the loop is on, the YZ, and you look at the magnetic field, what is phi when we're just in that plane, when we're just dealing with the plane that the loop is in?
Would it just be that whole plane wrapped around the z-axis?
Yeah, so if we were to imagine, like maybe it'll be a little easier if I redraw this. But let's look at this so that the wire, so we have this current. So the current is going in the z-axis. And then we have in this direction, we have y. And the loop is here. And then we'll look like this. We'll rotate it and so that x is out of the page. So if you, using the right hand rule, right? Let's take our thumb and our thumb should be pointed in the direction of the current. Okay, so our thumb goes in the direction of the current. And on this plane, so if you're on this side, does the magnetic field, take your fingers and your fingers point in the direction of the magnetic field, right? Their fingers point in the phi direction. So on this page, is the magnetic field going into the page, out of the page, or some other answer?
I would think into the page.
Yeah. So, and why do you think that? Cade, can you explain a little bit?
Because if I have my thumb up in the Z direction, my fingers curl around into the page on that.
Yeah. So on this side, it'll be into the page. And what would it be on? Oops. Apologies. And what about on this side?
Then I have out of the page on that side.
Yeah. Okay.
Doesn't matter. That's the way my fingers are pointing when I wrap it around.
Yeah. Who else agrees? Daniel, Gabriel?
Yeah.
Okay. So when I put my thumb onto the current direction and I have my fingers are always pointed in the direction of the magnetic field. So if I just imagine that my thumb is around like a bar or a pipe or something, and I wrap my thumb around it, I can see that on this side, it's actually pointed straight into the page. So my fingers are straight into the page. And my fingers, right, the fingers point into my fingers point in phi. So on this plane, where the loop is, what is phi? What could phi be in Cartesian? What could we convert it to in Cartesian? So what's the direction into the page in Cartesian?
X.
Positive X or negative X?
Negative X.
Yeah, so the X is out of the page. So it pointed into the page is negative X. Okay, now what about R? So R is out this way, right? So what could we say that R is equal to, where on the plane where our loop is?
Positive Y.
Yep. So now I could substitute in, right? We had this expression for phi, or for the magnetic field. And I guess I'll page. And what we just determined is that where the loop is, so we can rewrite this . All right, so do you all see what I did here? I substituted this in here. And this into here. And now I have an expression, right? And this is in Cartesian. All right, so keep this in mind. The reason that we did it this way, you can do it either way, right? You could solve this in Cartesian, or you could solve this in cylindrical. But I want to point out something and the reason that I did it this way. So first, if you think, what's one of the most common ways that current is carried? Like when you're building your breadboards, how do you often think of what is happening on the, like what's carrying the current when you make something on your breadboard? It's usually like a jumper wire or something, right? You have all kinds of stuff connected together on your
I
breadboard.
say like a conductor.
Yeah, a conductor and a so yeah, actually even better, Kate. Yeah, current. You're almost always going to think current is carried in some kind of conductor, and one of the most common conductors is a wire, right? And so if you have a wire, and this is in a lot of electronics, right? The wire you might then think of as being very, very thin, so thin that it's just basically a long, thin wire. And if we're looking at something very small, right, we might often think of the wire as being quite long compared to what we're looking at. So because of that, when we're modeling a lot of things in electromagnetics, we're going to be considering infinite wire case. And so if you have current in an infinite wire and it's an AC current, then that's going to generate some magnetic field. And so there's this case, right, where we have current often being carried on an infinite wire or a very long wire, and it's AC current, which means that we'll have some magnetic field associated with it. So AC current on a long wire is often associated with a changing magnetic field. And so in these problems, we end up using, it's very convenient to find the magnetic field of a long wire, right? We could solve this using Biot-Savart. You could solve this using Ampere's law. Like we've done both, right? So this is a common result to find. And because of that, right, there's a lot of problems or situations where you might be given a wire with a current, and what you should immediately, a wire with an AC current, and you should immediately think, okay, this has this magnetic field that's well known from this result. And often you have a wire that is, and we know the wire magnetic field in cylindrical, but a lot of other things in the problem might be in the more conveniently expressed in Cartesian coordinates. So this may come up again. It's a common situation where you have the magnetic field due to a wire, which is commonly known in cylindrical coordinates, but you have another structure that's square or rectangular, which would be more easily expressed or examined in the Cartesian coordinates. And so switching between the two, or choosing which coordinate system you want to work with, is important for these types of problems. So I think it's a little bit easier to do this in the Cartesian coordinates. Now that we have this, right, and we already saw we want to find the VEMF. So we know from the problems we just did that the VEMF is going to be d dt like this. All right, so we just found B. Now, what about this? If we wanted to find this loop, okay. If we want to find the area on this loop, what ds should we use?
dy dz.
Okay, dy dz. In what direction? So this is a vector. So what would be the hat in front of it?
Negative X.
X, right? Okay, and so if we have these two terminals here, terminal 1 and terminal 2, which one should we code as the positive and which one should we code as the negative?
Would 1 be negative and 2 positive?
All right, so let's point. So the fingers point from positive to negative. So
Oh, then 1 would be positive and 2.
yeah,
Because I put my thumb in the into the page.
yeah. If your thumb's into the page, then it would go the other way. So I'll change to, let's say, purple here. And then you would have it like this. Okay, so this will help you determine that reference. Okay, so now you know DS and you know what the reference voltage is going to be. So you should be able to solve for this. And then how many loops of wire are there? Just the one, I think, right? We just have one. So on this problem, n is equal to 1. Let me think if there's anything else that I want to point out. Don't think so. Do you feel confident that you could solve the rest of this problem?
Yeah.
Okay. So this problem, right? This in the first problems that we did today, right? We were given, right? It was very simple to get the magnetic field, right? It was told to us. This problem is really not that much different than the ones we did earlier. The only difference was we kind of knew what the magnetic field was, but we had to set things up to make sure that we were dealing with all the correct coordinate systems. Okay. So you'll solve for the V EMF, and then you will get some current that's in here. And you have some resistor, right? This one. So you'll be able to solve for this. You determine the magnitude that the current would flow, the direction and the magnitude that the current would flow. Okay. So because you have the reference now, you'll be able to find the direction and the magnitude because you'll have a reference point for this current. All right, any questions? All right, so the homework and the quiz are on Thursday. Next week, we'll do some review, take the exam. The other problems, 2 of the other problems from the homework 8, I have made videos of them, tutorial videos. So just like what we would do in class on Thursday, those are available for you. And then later today, you'll see a practice exam 2 that I've uploaded with some more problems that you can work if you'd like. So feel free to take off. If you have any questions, I'll stick around and happy to answer those for you.
Thank you.
Yep, you're welcome. Have a nice day.
Thank you.
Yep, you're welcome.
Thank you.
See ya.
Wanted to ask about the project.
Okay, yeah, project.
Yeah,
Okay,
you said we meant to estimate the voltage that will be produced from our project.
yeah, so you'll have a voltage that you'll produce on the with the project. So you'll use some human power, so a crank or something, to produce a voltage. And then you'll
Yeah.
use that voltage to turn on a small light. And that could be whatever type of light you want, but LEDs are probably the easiest.
But before we like physically build it, you said we have to like solve it and give like a theoretical estimate.
Yes, yeah. So the theoretical estimate, yes, you can find the theoretical estimate just like what we have been doing, right? So for this, you'll have to estimate the magnet strength. For this, right, you'll have to estimate your loop size. And then for this one, you'll have to estimate your motion, right? And then this one, you'll have to estimate the loops.
So how do we get like the B field changing with time? How do
Yeah, so you'll, this is up to you to try. So I would just try Googling. You don't have to get the exact answer, but I'm just interested in seeing what your answer, your result might be. So the way that I would do it. So I don't know, let's just say you have a neodymium magnet. So there's some of these. How do you measure the strength of a neodymium magnet? So there's just, you could search this up. There's probably a number of different ways that you could guess the strength of this magnet. So you don't have to get an exact answer. But you can see that it will generally be based on the size, shape, grade, and where the measurement is performed. So I'll leave it up to you to determine how you might be able to estimate that. Does that answer your question?
Yeah.
Okay. So this is the first time I've asked students to do this. So so I'm not sure how difficult this will be. So, but I just did a little bit of searching myself before I wrote it up that way. And I think that you can probably come up with some kind of a estimate. It doesn't have to be exact, but just come up with an estimate. And then when you're writing your report, you'll explain why you made the estimate that way.
For the motional EMF, just like estimate the speed of the loop, the way it's moving to the field.
I think so. I know I've said this before, but I have a very, very hard time understanding what you're saying. I don't know if your microphone is like a long ways away from your face, or if it's like dirty or something, but it's often very hard for me to understand exactly what you're saying.
My mic's stuck in front of me, but I don't know why it's always coming out.
Yeah. So basically that equation that I showed you, that's how you find the EMF voltage, and each aspect of that can be estimated. And if, depending on how your project looks, you might be able to measure the voltage and come up with that estimate. I would also say too that it might be easiest to estimate the peak voltage. So you don't have to estimate the time varying voltage. You can just estimate the peak voltage.
Thanks.
Yeah, you're welcome. Any other questions?
No, that was all.
All right, you're welcome. Hope you have a nice day.
Yeah, you too.
All right, bye.